Today we are going to see some of the memory elements, whatever we have seen in the last class. Extension we are going to see, right? Okay, memory elements. So let us recap once again what we have learned. Memory elements are essential component for the sequential circuit design, right? Okay. So if you talk about any sequential circuit, how do we how do we define a sequential circuit? If I say a digital system is realized with sequential circuits, means what? The output of the digital system depends not only present input, past history of the input also must depends, right? So in order to get the past history of the input, we have to take the combinational circuit. Okay, apply the primary input here or present input here, and we will get definitely the primary output or present output, right? If you want to make this as a sequential circuit, what we have to do? We have to add a memory element, right? Because we want to store the data of the previous output, right? So the moment if I'm applying the some input here, you will get that output, and that must be stored in memory. And the next time, whatever the input that you apply, that if you want to get the output of this one, definitely you have to apply this input also. Okay, are you getting this point? So therefore, this is what the memory element. Memory element. So what are the different memory elements we have seen? It is a sequential circuit. So this is called the next state. This is called present state. Okay. If the function, the output of this particular state is a function of both primary input and present state. Okay, if you want to get the output of a sequential circuit, both inputs are required, right? Okay. Now let us see what are the memory elements we have seen. What do you mean by memory? It is the ability of the device which can store the data, right? Okay. What are the different types that we have seen? Latch is one memory element, and flip-flop is another memory element, right? Okay. So how do we define a latch? In the last class, we defined about the latch. Okay, let me recall that one once again. What is a latch? So if you take a simple latch is nothing but D latch that we have seen, delayed latch. When the input is given, it takes some time and it will produce an output. Okay. But that input will transfer as an output based on enable signal. Okay. Without enable signal, it cannot. Okay. So let me take this is let me call this is a D in, and this is called D out, and this D in will D out will take the D in input as an output, provided there should be one enable signal. Without this enable signal, it cannot transfer, right? So this type of okay, I want to discuss this one as a positive D latch. Okay, D latch. D latch. Okay. Now, what is the functionality? How do we define the functionality? As I mentioned, we need to have enable signal and DN signal. By these two input signals, we want to calculate or we want to derive the output, or we can define the output, right? D out. Okay, what is the D out here now? If enable signal is not there, whatever the DN signal it is there, it does not depending upon whatever the previous value of the output is there, that output will be remains there. Okay, this is called D out, unchanged. Okay, previous value. The moment if you give the enable signal is 0, okay, and then if you apply the D input signal, okay, in this case also, I don't want to transfer the DN signal to output side, but let it be the previous value only. Okay, this is also previous value. But whereas when you apply the enable signal is 1, if you apply whatever the DN it is, the logic 0 or the logic 1, okay, however the input it is, that will be transferred as an output. Okay, so which one is the storing case? Where we are able to store? We are storing the data when the enable signal is 0. Okay, we are storing the data here. What we are doing here? Transparent. So that's the reason why it is called transparent latch. We can call it that. Okay, DLATch. Okay, this is what the logic that we have learned in the previously, and I have given. Of course, I have written the Verilog code for this one also. Okay, and I told you that how it is happening in this one. Okay, let me just a small thing that I will write here. Verilog program I will write, and then I will go. What are the additional things that we can involve in it? Okay, look at this one. So how do we write the program for this? According to this particular input-output behavior, how do I write? Module DLATch. What are the things? Enable DIN Dout. Okay, what are the inputs here? Very good. It's enable DIN. What is the output here? Output is, since we are going to write the behavioral modeling, as I told you that whenever the output is depends upon the previous value, that means storing elements is there, definitely there is a input to output connectivity will be there. If the input to output connectivity is there, definitely behavioral modeling is the best choice when compared to the data flow modeling, some other things actually, right? Because this will run under the concurrent program execution, right? That's the reason why. So that's the reason why we would like to write it in the behavioral modeling. Therefore, whenever you write the behavioral modeling, output must be in the register data type. Okay. And one more thing is that since it is a behavioral modeling, we have to use always block. Always output will changes on what? If enable signal changes and DN signal is also changes. Now let me write begin and end here. Okay, what is the alternative way that I have written? Simple approach. If enable is true, if enable is equal to 1, then D out is equal to DIN. As simple as that. If the enable is not defined, then whatever the previous value is there, that will be there in it. As simple as that. Therefore, the 2 or 3 variants that I have shown you previously, right? Well, this is a simple way that we can write. Okay, I'm not going to discuss again more and more on this. Okay, and module. Okay, hopefully everyone catch this point, right? Every statement is I have explained clearly in the previous class. Now, today let us go and take one simple example. Okay, what is the problem in the DLATch we found? Storing time is less. Okay, storing time is less. That means only half of the cycle that we are able to store the data, but not full cycle. Okay, so let us see how to solve this problem. First of all, let us take the input signal is something like this. Okay, this is the enable signal. Let us consider this is my input signal. So assume that this is the DN signal, right? Okay. Now please let me know what is the output of this one? If this is our logic that we have written, according to this one, let me know what is the output. What about here? So till this point, enable signal is on 0. That means the previous value it will hold in this particular one. Okay. Then this value is equal unknown. Okay. Till this point is unknown. Okay. Okay. But exactly at enable is equal to 1, what is happening here? If the enable is equal to 1, input as transferred as an output. Therefore, let me write here is this is 1, this is 1, till this point, right? Okay. Now, since here, what is the enable signal here? 0. That means previous value will be there. The previous value to this particular one at this instant of the time, what is the previous value? Just delta t of the previous value. Okay. That will be continued, right? I'm going to take, for storing purpose, I'm going to take this one. Okay. Now, what happened here at this time? So this value is equal to 1 to up to this point, and then now go down and give you a transparent to this particular one, right? Whatever that is there, that will be transparent to this point. Okay, at this point, what you can see, again, you see the logic low value. Whenever the logic low value is there, previous value will be continued. Okay, next, what happened here? What is the next one? Since enable signal is equal to high, the input is transparent. Let me transparent this. Right? Okay. Since the enable signal is 0, so that will be continued. previous value is continued to this point. Okay, what about the next one? It will be go down, right? Sorry, high value only. So till this point is over, and we'll go here. Oh. Agreed? Okay. It must be very, very careful when you are drawing the waveform, right? So this is what the transparent region. This is actually here what information that we stored here? Logic 1, right? We stored here is logic 1 we stored. What we stored here? We stored logic 0. What we stored here? Logic 1, we stored logic 1. Okay, remaining all cases are transparent. Okay, so this is the positive latch. Okay, the transparency, the positive latch mode is related to the transparency. When the logic 1 is there, the transparent input to go input to the output. Right. So therefore, during this entire cycle, what we can see that, so the enable signal from low to high, this is the entire cycle, only half what we stored and half what is transparent. Are you get the point? Now the question is that I want to store the entire the period of the enable signal. Okay. So therefore, a single latch is not possible. Okay, by combining the single latch or the two latches, it is possible. Okay, but people, because if you're using to do this kind of things, the hardware cost is more. That means more number of latches are required. Therefore, we don't want to go and do this kind of approach. Instead, what we do, we go and realize with flip-flops. Another memory element that is available, that is called flip-flop. So let us see what is the flip-flop and how it will be doing. How the flip-flop is able to store the data. Okay, so the moment if you're talking about the flip-flop, then instead of calling this as an enable signal, this is called as a clock signal. This is called as a clock signal. The moment if you're talking about the clock signal, and we always talk about the edges of the clock, not on the levels of the clock. Okay, that means we need to talk about the edges here. This is a positive edge is there. You can concentrate on either the positive edge or negative edge. Okay, for the time being, we talk about the positive edge. Is the positive edge. This is another positive edge. This is another positive edge. This is another positive edge. Actually, the clock is nothing but enable signal only. Just for identification purpose, we are writing this is the positive edge, this is the negative edge. Because we want to transfer the data based on the edge, not on the level. Okay, the transparency occurs where the edges of the clock signal or enable signal. Okay, yeah. So now accordingly, let us derive the truth table for this one. Okay, we have a clock signal. We have a clock signal. We have a DAN signal. Let me derive the truth table for this one. The clock CLK also I can usually people will write CLK. Whenever you see the clock signal, people instead of CLK short form they will write CLK. The shortest notation, right? Okay. Let me write it the way same way. The clock CLK and DIN and D out. Okay. If the clock is not given, irrespective of whatever the DN it is, okay, the output is the previous value. It is the same as that of the latch also. Okay. Okay. Now, whenever you see a positive edge, whenever you see a positive edge, then whatever the DN that you give, the DN will be transparent. Okay, this is DIN. Okay, for all other cases. Okay, for all other cases, other cases. Let me talk what is the other cases. DN, if whatever the DN it is, it should be the previous value. It should be the previous value. So what is the all other cases in this case? Let me write. What do you mean by all other cases of the clock signal? Level. It may be a positive level. It may be a negative edge. It may be low also. This come under all other cases, except the positive edge. For all other cases, high value, low value, negative edge, we don't bother about it. For all the other cases, what it will be? It will be DN, the previous value, right? So this is called a flip-flop. This is called the flip-flop input-output behavior, right? We take this is one. Okay, let us go and apply on this one. Shall we draw the clock signal for this? What is the this is called D latch output. Okay. Now D flip flop output. Let me call this the D flip flop. DFF stands for D flip flop. Yes. What will happen here? Can someone help me according to this truth table? In the first one and the first case, you find that the negative, the low level, it will come under the last case. It is come under the last other case actually. Okay. For other case, D out is equal. The D out is nothing but D out, the previous value. We don't know the previous value since it is a memory element. Therefore, it is same as the thing. Okay. Now, at the positive edge of this one, what will happen? At the positive edge, that means it is a sharp edge. Okay, at the instant, what is the value that is available? As you can see, at this instant, you can see only this one, right? That is the logic one is available. Logic one is available. So that logic one will be attained. Okay. It will be available till the next positive edge. Okay. So therefore, it will be available till the next positive edge. Because in between, whatever it is there, we don't bother about it. Why? Because it is come under the other case. For other cases, the previous value. Okay. So therefore, here it is assigned here. So when we come to this particular time to this particular time, what is happening here? The previous value to this point is nothing but this one only. Okay. That will be continued. Okay. Right. Now at this edge, what you can see? Logic 0. Okay. Therefore, the logic 0 is assigned with this. Okay. Logic 0 assigned. And this is what the value that is available, the D out now. Okay. For the next case means what? Next case, high values. So for the high values, what it will come under? Other case. Other case means that the previous value. Already D out is available within it. Therefore, that will be continuous. Okay. So therefore, this will be continuous for the next positive edge. Okay. Now at this positive edge, what will happen? What is the input here? 1. Okay, therefore, it will continue to 1. So this is assigned to 1. And that 1 is continues to the next clock. Now, what about here? At this positive edge also we can see one only. So therefore, this one is again that is assigned here, that is assigned here, and that is continues to the next and next positive edge. What is happening here? Assigned, and for all other cases, it will be continuous, the previous value. Hopefully, you catch this point. Okay. So this is what we call it as. See, look at this one. How much amount of the time that we are able to store? We're able to store here till this time. Logic 1 we stored at this point. Okay. Logic 1. What we stored here? What we are able to store here? Logic 0 we were able to store logic 0. Here what we can store? Logic 1. Here also the logic 1 only. This is also a logic 1. Also logic 1. Okay. Therefore, the entire cycle is we use it for storing. Only at the edge only we are talking about the transparency. Except the edge, all other times are we're able to store the data. This is what very tempting to use in our digital circuits. Okay. So, but realizing this D flip-flop by using the gates is actually complicated. Okay. Therefore, we don't want to use this particular one by using the data flow modeling or some other cases. Equations are a little bit difficult, and gate-level circuit is also difficult. Therefore, better we go for input-output behavior, we know, and the Verilog has given a provision to write Verilog code by looking at the input-output behavior. Okay. So let us write the Verilog program for this. Okay, let me take this the same program, and I want to modify this program. And please help me how to modify this program according to the logic that I have shown there. Yes, people. So instead of the D flip-flop, let us take this as a D latch. Sorry, D latch instead of D latch, we write D flip-flop, DFF. Okay. Instead of the enable signal, what we can write? The clock signal, CLK. Very good. And here also we need to change CLK. Output is same as this one. And now the question comes is always block. Okay. What should be the sensitivity list? What should be the sensitivity list? The output is changes only on clock signal. We don't bother about the changes of the DN signal, right? Okay, because at the edge, the changes are not relevant to us. At the edge means that only 1 point only at the edge. In the edge, we cannot see so many changes, right? Okay, so that's the reason why whenever this edge, we can see only either logic 0 or logic 1, not that it is available so many things. It won't work. Okay, right? So that's the reason why only one value is there. That's the reason why only the positive edge is required for us. The changes of this one is not at all required. That's the first thing. And we have to use enable signal instead of the enable signal. We have to use clock signal. But what clock? If you write the clock here, the meaning of this one is either the changes of this one, either the 0 to 1 or 1 to 0. The changes can be 0 to 1 or 1 to 0. The clock means that the change we are talking about, right? We are talking about the change. Change of the clock means what? Either logic 0 to logic 1 or logic 1 to logic 0. This is what we are talking about. Which one we are talking about? Whether the 0 to 1 change we are talking about or 1 to 0 we are talking about. Positive edge, 0 to 1 change. Therefore, in the Verilog, we have a provision to use this one with the help of pause edge. It's a keyword we can use it. It is a pause edge. We have to use pause edge clock signal. Madhotna. Okay, next. So now how do I write the program? Okay, therefore, whenever you see a positive edge, what has to happen? Whenever you see a positive edge of the clock, whenever you see a positive edge of the clock, you look at this. D out is assigned with DAN, right? Okay, therefore, we are now going to write, we are not going to check anything here. Okay, I mentioned that only the positive edge only. Okay, whenever you see anything to the positive edge, it will enter into this one and execute some statement. What is that statement here? Simply D out is equal to DAN. D out is equal to DN. Whenever you see a positive edge, enter into the block and assign the thing. When there is no positive edge of the clock, don't enter into this always block. Okay, and whatever the previous value is, the previous value continues. Is this point is okay? Any question? Not required. Why? Already positive edge is mentioned. It is a redundant term. It should be. Okay. It is not required, right? Okay. If a positive is the positive, this statement is not actually not there. If positive edge of clock. Okay. That is what we have written in this one. This is the way, that is what the meaning. What is that? Work out. Okay. Okay, so this is what we need to write. Since it is a begin and is not required since only one statement, right? Okay. Okay. So look at this one. Let us apply this program. How this program will be executed. Okay. See, first of all, you check that whether the positive edge is there or not. Okay. So according to this particular test scenario, okay, you have given the no positive edge here at this point. That's the reason why it cannot enter into the always block. That's the reason why it will be unknown. This point is okay. It is unknown. Whenever you see the positive edge, okay, the change is observed, that to a positive change, okay, then what will happen? It will enter to the always block. In the always block, what it is there, whatever the DN is there, that will be assigned to D out. Okay, therefore this value is assigned to D out. Okay, this value is assigned to D out here, 1. Okay, next, at this one, okay, there is a high level. This is a high level. So is there any change in this always block? Is there any change in the sensitivity list? No, there is no change. Therefore, it cannot go to the always block. So therefore, it will go. It cannot go to the always. So therefore, the previous value will be 18 till this point. Okay, till this point it will be there. Now we can see there is a change. But what change? This is a negative change. But what we expect a positive change. Therefore, it cannot go enter into the always block. Therefore, it will be remains in this particular one. Now, as you can see, there is a change here. What change? This is a positive change. Whenever the positive change means, it will go into the Always block. Always block what we mentioned, transparency. That means whatever the D input signal is here, the D input signal will be transparent at this place. Okay. Now the same thing will be continuous. Hopefully that you catch this point, right? Therefore, by writing the waveform, we can derive this the program, and based on the program also, we have to analyze that waveform, how it will be executed. Also, you should know. Okay, right. Now let us go and write the test bench for it. Right. What is the test bench case that we have written? Okay. Okay. Let me go and quickly write the test bench as well. Okay, this is a 0. This is 5 nano, 10, 15, 20, 25, 30, 35. Okay. Now what let me consider this is 1, 2, 3, 6, 7, 8, 9, 11, 12, 13, 16, 17, 18, 19, 21, 22, 23, 26, 27, 28, 29, 31, 32, 36, 37. So just conventionally, whenever there is a change, I have mentioned the delay values. Okay. Whenever there is a change, I mention the delay values. Okay. How to start this particular test bench? Okay. Module. D flip flop underscore test. Reg clock comma DN. Next reg. Sorry, Y, right? Yeah, thank you. The Y D out. Okay. Next, first the initial. Always let me write the always block, for example. Oh, no, initial. Let me write the initial. Initial. Let me begin. What we can write there? What is the first clock signal? CLK is 0 at 0 nanoseconds of time. Next, DN is also 0, 0 nanoseconds of time. Okay. Next, what we can see here at 1 nanosecond, high and 2 nanoseconds low, high, low. Okay. At 1 nanosecond, DN is equal to, okay. At 1, DN is equal to 1. Another 1 nanosecond, DN is equal to 0. Another 1 nanosecond, DN is 1. At another 1 nanosecond, DN is equal to 0. Okay. At 5 nanoseconds, the same value. Okay, till 6 nanoseconds. Therefore, at another 2 nanoseconds, DN is equal to 1. Is it 1? 2 nanoseconds, 6 nanoseconds, it should be 1, right? No, 6 nanoseconds, it should be 0. It should go down to 0. Okay, what about this one? 1. What is this there? 1 it is there. So the 2 must be 0. 2 must be 0. Okay, the 2 must be, yes, 2 must be 0. What about 3? 3 must be 1. 3 must be 1. Okay. What about the 4? 3 must be 1. Okay, the 4 and 5 both are 1 only. So this is actually, don't worry. For the 4 and 5, that means 1, 2, 3, 4, 5, 6. Okay. This value becomes 0. Okay, you continue this one. Okay. Till whatever the waveform that already we have in the last class, we have seen that one. So let me end this one. Okay. You know that you know very well about it. Okay. Next two. What is the next one? Always block I have to use. Always. For every 5 nanoseconds, clock is equal not of clock. Right? Okay. Next. These signals must be applied on what? D latch, right? Sorry, D flip flop, right? It's a D flip flop. It's a module M0. Okay. What is the value? What we have to write? Clock DAN D out. Okay. And I want to stop the simulation when I want to stop the simulation. I'm going to use initial block again. Initial dollar. Sorry, hash. At what time that we can stop the simulation? For example, at 40 nanoseconds. Okay, 40. I can directly write 40 here. 40, and it should be dollar stop. It is a system task. It will stop the simulation. Finally, end the module. Did you catch this point? It's very systematic, right? Okay, first initial block I have written, next always block I have written, and these input signals are applied on this particular block, and then I want to stop the simulation at this particular time. Okay, hopefully everything systematic. Whenever you write a test bit, this is the approach that you follow, right? So far, so good. Okay, of course, you can the one line statement. Therefore, I'm not going to time to execute this one. I'm going to go another concept. Okay. Now let us go and introduce one extra signal to the flip-flop. Okay, let me write what is the flip-flop here now. Okay, as we have seen, D flip-flop. Okay, without a reset. Without reset signal. Okay. So if we talk about any digital circuit, okay, if we talk about this is the memory element, for example, as we have seen, we have a DN signal, DAN signal, and it will produce the Dout signal, provided there should be one enable signal. One enable signal. So this signifies that this is the edge we are talking about. Okay, since we are talking about the edge, based on the edge transparency is there, it is called flip-flop. Okay, therefore it is a clock. It is a clock, CLK clock. Okay, so this is called positive edge flip-flop. Positive edge flip-flop. If you want to make it as a negative edge flip-flop, for example, what you can do here, that means the transparency should be there at the negative edge. For all other cases, it will be previous value. Then what is the change you have to see in this program? Yeah, instead of the positive edge, what we have to write? Negative, right? So instead of doing this, what I can write? Negative. Okay, that's only the change, nothing else here. Right. If it is a negative edge, then for example, then what we can do? If it is a negative edge, then instead of writing this clock in this way, use the bubble there, and then write a signal here. This is the clock signal. Okay, always remember that one. Based on the edge only, we have to say that's a clock signal, or the edge only we can say it is a flip-flop or latch. Okay, so now can you differentiate between the latch and flip-flop? What is the difference? It's a level sensitive. Okay, that means if it is a latch, based on the level, the transparency occur. Okay, but whereas in the flip-flop, based on the edge, the transparency will occur. Okay. Now, the general sense is that, okay, based on the clock signal, the transparency is there, storing is there. Okay. But unfortunately, what will happen in this case is, since it is a memory element, because there is a input-output connectivity is there inside of the flip-flop. Whenever you switch on the power supply to this particular flip-flop, some unknown value will be there here. Okay. And from that unknown, we are starting to bring into different things. But what we want to do it, the moment if you switch on the power supply, you have to clear all the content of the flip-flops. You want to make zero or maybe clear all the content of the garbage. Okay, first you clean it first of all, and then apply the clock signal and do that thing. Is that clear? So therefore, we are going to use an extra signal that is called reset signal, RST. RST stands for reset signal. Okay, the short form that we write RST. Okay. When the reset is there, then all the content of the flip-flops must be zero. That means, as I mentioned, that is just like you imagine this is a bucket, for example. Okay, there is some garbage which is available there. Okay, some garbage is available there. Okay, then if you want to make use of this one, what you have to do first of all, in your home, then you see some parts, for example, right? If you want to make use, what you have to do, first of all, you have to clean at least. You put it in the tap and then you have to clean it, and then you have to use pour some new things on that one and then make use of it. The same thing only, right? Okay, just how can you make this thing? How can you clean this one? By applying the reset signal. Okay, so therefore this is the reset signal. Let us modify our truth table based on this. Let us apply truth table on this. Let me copy here. Okay, and I don't want to use this because the name I have given differently. That's the reason why I'm using the same name with, okay, without a reset signal. Without reset signal. Here is with reset signal. Okay. Keep it here. Okay. Now you copy this information. Okay. And then paste. See, look at this point. If it is a negative edge, what is happening here? If it is a negative edge, it should be negative edge. It's a transparency, right? Please remember this thing. Okay. Yeah. Now, what additional thing that we have to add? Additional thing we have to add is
RST, reset signal. Okay. Right. Again, here, if you're not using a reset signal and the clock signal, whatever the DN signal, okay, the previous value will be there undoubtedly. Okay. Now, when you switch on this one, now you make this RST is equal to 0. RST is 0. Now, whatever the clock signal it is, whatever the clock signal, whether it is a positive edge, a negative edge, or it may be high level, low level, it doesn't matter. And whatever the value of the DN it is, okay, any changes of the DN also, the value of this one is 0. This is 0. Okay, that means the moment if you see, of course, I'm so sorry. Okay, but I want to talk about the positive edge of the positive value of the RST, not negative value of the RST. Okay, you can take the negative value also. For the time being, I'm not going to talk about this one. It is the, let me take here. It is the 1. RST is equal to 1. Then it should be 0. Whenever you see the RST is high, which means that clear the contents of the flip-flop. Okay. If the RST is not there, then if you find the positive edge of the clock, then whatever the DN is there, the DN will be transparent to this one. Did you catch this point? Okay. If you are confusing with this particular statement, you keep it aside this particular. For the time being, just you don't consider this one. Okay. Don't consider this one. You consider this one. Okay. If the RST is 1, irrespective of the clock signal, irrespective of the DN signal, the output will be 0. Is this point is okay? If the clock RST is not there, RST is not there. Not there means that RST is 0, for example, or for any other cases, I can say, instead of saying that it is 0, for example, RST is 0. Okay. Then, depending upon the positive edge of the clock, whatever the DN is there, the DN will be transparent. Okay. Right. Now, the last case is RST is 0 for all other cases of the clock. Other cases of the clock, whatever the DN is there, we don't bother about it. It should be the previous value. Is this point is clear to everyone? Okay. Okay, therefore that's the reason why it is meaningless to write this particular statement without making things are very complicated. Okay, this is a better way actually. If the RST is 1, what will happen? The output is 0. If RST is not there, then think about the clock. If the clock is 1, the output is, if the clock is positive, transparency occurs. If the clock is other cases, previous value will be there. If this point is clear, that means out of this clock signal and reset signal, which one has the topest priority? RST having the highest priority or clock has the highest priority? RST has the highest priority, because unless otherwise the RST is high means that don't bother about other signals. Okay, that's the reason why it is called asynchronous reset. What we can call it as asynchronous reset. That means the RST is not synchronization with the clock signal. Okay, it's independent RST actually. That's the reason why it is an asynchronous. It is not synchronization with the clock signal. It is asynchronous to the clock signal. Synchronous means that okay, the mutually both must be there. Then only the things will be happen. Okay, I don't want to consider the other thing. only I am the toppest person, then he will go accordingly, means that he is a synchronous person. Okay, so therefore it is called asynchronous reset. So far whatever we have seen, this is called asynchronous reset D flip-flop. Are you getting this point? What do you mean by asynchronous reset? Asynchronous reset means that it does not match with clock. It does not communicate with the clock signal. Okay, that means it has its identity is there. According to its own identity, the flip-flops will be clear. Okay, right. So let us write this program. Okay, okay. Let me go and modify this program only. Okay, then we will go and apply this concept on the waveform. Right. Let me copy this. Okay. Okay. Now again, I want to take this as a one. Copy. Okay. Yeah, please let me know what change that I have to write here. Everybody knows that reset is also required, right? Reset, let me write the reset also, RST, reset. Okay, now we have to add RST as well. Let me come here, RST, of course, let me go in a better way. Okay. First RST means that let me write RST first. RST, okay. Output is registered at type only. Now, how the output is changes? Whenever you see a change in clock signal, whenever you see a change in reset signal, output must change. That means I have to have both signal, RST and clock signal. So you look at this particular one, what we can see, RST is a positive, only positive edge we are talking about. What about RST? We can write RST. When the RST is height, we are talking about, right? But actually, this is what we normally see in this particular structure. One is a positive edge, next one is a level sensitive. That means one value. No positive edge, is a level sensitive. If I'm not writing this edge, means that it's a level. Okay, that means there should not be, the sensitivity should not be like this. Either it should be a level sensitive, both the signals, or edge sensitive, both the signals. We should not write one is a edge, next one is a level. You should not write it. Verilog does not give this kind of provision, right? We have to write the reset is also edge related. Okay, that's the reason why I'm going to talk about this is also an edge. Okay, whenever you see a positive edge of the reset, then you see a positive edge of clock, and you also see the positive edge of reset signal. Okay, so for now I'm going to take this little bit out, and I'm going to write positive edge of reset. Is this point is clear? Okay, that means you have to see the positive edge of the clock and positive edge of the reset, then only you enter into the clock signal. Sorry, enter into the always block. Now in this always block, what you have to do? That's the question. Whenever you see a positive edge of the clock or maybe positive edge of the reset, you enter into this one. Okay, that means you look at this one. Look at this. I did not mention it is an edge, right? I did not mention it is an edge. What it is? One. It is a level I'm talking about. That means whenever I see, okay, there is a change in the clock signal, change the reset signal, you enter into this one. And if you find the reset is 1, then the output must be 0. If the reset is not high, then the D out is equal DAN. Look at this one. Let me write this statement. Okay. If RST is true, if RST is 1, then Q is equal, sorry, then D out is equal to DAN. Then D out is equal to DAN. Okay, that means this is the statement that we have already completed. This statement we have completed. So I don't bother about the clock signal, whatever it is. No? Yeah, so sorry. Yeah, D out is equal to 0. Very good. 1 bit of 0. Thank you. Next. So the first condition is over. Okay, we have given the topmost priority. Whenever there is a change, immediately enter into this one. It will check first. It will check first RST. Okay. So therefore, we are given the topmost priority to the RST now, right? Okay. If the RST is 1, make it 0. If the RST is not there, then so depending upon the clock signal, already positive edge is there. Already positive edge change that we have seen previously. Based on the positive edge, the D is equal, D out is equal DAN, right? Okay. Therefore, else statement I can write here. Else. I'm so sorry. This is the keyword, right? Else D out is equal to DAN. D out is equal to DAN. No, you should not write else if clock is equal to. You should not write like that. Because already the positive edge of the clock is there. Then only you enter into this one, right? If there is a change in the positive edge or reset is there, okay. Maybe first time it is not there, for example. Look at this one. It is not there, for example. Only this change is there. Okay. You enter into this one. You enter into this one. Now what will happen? Reset is not there. Positive change is there. Okay. Then immediately RST is also positive change means that RST is high. Therefore, this value is 0. And it cannot go in the else statement. Okay. Now, if the positive, if now this is not there, for example, this is not there, for example, this is only there, for example. Okay, then even you enter into this one. Okay, if the positive RST is there or not, you check that. If it is there, for example, then 0 will be there. If it is not there, then since if the positive of the clock only you enter, according to that one, the DN will be assigned to D out. Okay. Now this waveform, based on the waveform that we can get more insight of this one, whatever I told you, that one, we look at the waveform and then wait for it. Okay. Let me take this same waveform. Okay, let us analyze this. This is the most important, and whenever you have interviews, people ask you and irritate you this kind of asking these questions, and they will. Okay. What is the time now? Okay, now I'm going to do, I'm not talking about, okay, for to reduce this complexity, I'm not going to use this particular D latch, okay? I'm removing this D latch. Okay. Now let me write in this way. Let me call this is the RST. Let me call this is an RST. Okay, D flip-flop without RST. Okay, D flip-flop without RST. RST, the output is this one, as we know very well. Okay, now with D, what is the output? D flip-flop with RST. What will happen? Now, according to our truth table, please let me know what is happening here. What is the truth table mentioned? What is at the 0 nanosecond step time? What we can see here? The clock is 0, DN is 0, reset is 0. What will happen to this one? It is unknown, right? It is unknown. Okay. So, okay, how long it will be unknown? Either the positive edge of the clock or reset unknown. Okay, till this point. Assume that in the first place we can see the clock signal. Okay, according to this waveform, first what you see, the clock signal. Okay, let me till the clock signal. I am going to have this particular thing. Okay, this is unknown. Okay, now what is happening to the next? You see the positive edge of the clock. Okay, so when you see the, okay, better I can take this waveform so that you people don't have any confusion. Let me take this. Copy, and I want to paste here. You please let me know what is happening here. Which condition that is holds good? The positive edge of the clock is there. Reset is 0. Positive edge is there. Reset is 0. Then whatever the DN is there, the DN will be transparent. What is the DN here now? It becomes 1. Okay, it becomes 1. Till what? To the next positive edge of the clock. So it is go and doing this way. Okay. Okay. Therefore, it's going something like this. But when it is going here, you see a change in RST. Okay. So till this point, 1 does not have any problem. But because of this RST, we are entered into this particular condition now. Okay. If the reset is equal to 1, what we said that the output must be 0. Therefore, it must be 0 now. It must be 0. How much time this should be 0? As long as RST is 1. Okay. This 0 as long as RST is 1. If this point is clear, we have to go till this point, but we have to go till this point only. At this time, what is happening here? You see, there is no RST, fine. Then we have to look at the clock signal, but the clock signal is also 0. That means it should be depending on previous value. So what is the previous value? This is only the previous value, right? So it will be available to the next positive edge of the clock. Is this point is clear? Okay. So in a waveform, let us look at this particular scenario in our waveform, in our program, let us see. Okay. So what is the condition here we have seen? Okay, sorry, here. What is the condition we have seen? What change that you identify first of all? Positive edge of the clock. Where you enter into this one, begin and enter block this one. Now RST is 1? No. Therefore, this is not satisfied. It will go to the else statement. Therefore, dn is equal to d, right? Okay. Then when you see the change again, there is a change that you can see again on RST. Okay, that means again it will, because of this RST now, it will enter into this block. In this one, RST is 1, right? That's the reason why it becomes 0. Therefore, it cannot execute this one. Again, there is a change in what? Again, there is a change in what? Is it a clock or RST? It's RST. It's going down. Okay, because of RST, there is a change in RST. That's the reason why it is going. Actually, no, because there is a change in this one, but it's not entered into this block. There is a change in RST, but it's not a positive change. What it change it is? Negative change. That is not entered into this block. Therefore, previous value will be continuous. There is a change, but it cannot enter into this one. Hopefully, you did catch this point. Huh? Okay, right. So what about the next one? Now we can see there is a positive edge of the clock. There we cannot see any kind of RST. Therefore, we enter into this always block. And in the always block, RST is not there. Therefore, reason why only depending upon the clock only, it will be there. Okay. This 0 is because of what? It's not previous value. Of course, I'm unable to give you the waveform in that much way, but I know the logic. That's the reason why I know this 0, why this 0 has come and why this 0 has come. I know very well. Now you also know about this one. This 0 is because of transparency. So this must be go till next positive edge of this one. Okay. But unfortunately, what is happening here? There is a positive edge of the reset signal. Okay, because of this reset signal, anyway that is 0. Therefore, from this onwards, whatever this 0 is responsible because of RST. But how long this will be available? As long as RST is available. Did you catch this point? Okay, so this 0 is because of transparency. Okay, this 0 is because of RST. Okay, because of RST, this is 0 because of transparency, PR transparency. Okay, now right. So what about here now? Here again, there is a change here, but this is a positive change. It's not a positive change, it's a negative change. And can you see any kind of change here? There is no change here. Okay, that's the reason why it will be continuous till the next change. Whatever the change that is there, then depending upon the next change, it will come. Whether the RST changing or clock is changing, that will be decided. Okay, so till this point, this is 0. Now what you can see here now, because of no RST, we have only the clock. That's the reason why it will go up and remains there to this point. Here, RST. Any question on this? You have got the clarity or not? See, so without RST signal, this is how the high and low, something like this it has come. But because of the RST, this is how the look like the waveform is something like this. Okay. So whenever you give the RST randomly, something like this also, okay, you should be in a position to understand how the waveform has come. Okay. Right. So that's the reason why we don't want to use RST the way that I have given, only for the explanation purpose and to understand, to face the exam point of view. I told you something like this, but nobody do this kind of the way you're using the RST. Okay, first initially you make the content of the flip-flop is equal to 0, and the remaining all the other cases, this must be 0. Okay, then depending upon the clock signal only, it has to work. Okay, that's the reason why I'm changing a little bit on this. Okay, what I'm going to change here now. So I keep maybe a small duration of the time. I keep this value 0, 1, and remaining all these things are 0. Okay, you take something like this and make it something, and keep it everything is 0. Okay. Initially make the RSTs high and then 0, and depending upon the clock signal, the operation has to go. Okay. So under this condition, what output that you can expect? So till this point, you can see that till this point, unknown, and then this becomes 0, 0 as long as RST is equal high. Okay. Now this will be 0 till the next two. This will be continuous because RST, the positive edge of the clock is not there. It will be remains there for some duration of the time, and then it go to high. Okay, I'm so sorry. I think till this point, I guess. Okay, and it will go as it is. Okay, right? Okay, we did not. Okay, so it is followed in the same way. Okay, high. Okay, so please remember that this is because of law 0. So unknown values, only one unknown value. After that, it makes 0. Okay, and then depending upon the RST, it has gone. Very important. Okay, so therefore I'm going to, I'm not going, so this is what you have remembered, but I want to say something also this one. Just only one thing that is required, and this. Where the waveform that I have written. Okay, let it be like that. The last concept on this, that is called synchronous reset. Last one is called synchronous reset. Just for 2 minutes. Look at this one. This is what I have given. Synchronous reset is the word that I'm using. That means the reset signal has an impact whenever there is a clock signal. When there is no clock signal, the RST does not have any impact. That means so far we have given RST is the topest priority. Then we have given the second priority to the clock signal. But now what we are giving, clock has the highest priority and reset is lowest priority. Okay, so let us look at this particular waveform now. Okay, because unfortunately I removed that waveform. That's the reason why this is also may not be correct. If to compare this, what will happen to this one? Okay, yeah, look at this. Now let me know what is the output of this one. So as we can see that we can see the change only at the we can see first RST has come. Sorry, clock has come. Okay, before the clock this will be unknown. Now there is a positive edge of the clock, and RST is also 0. Therefore, what will happen here? Transparency. It will take logic 1, and this logic 1 will available to the next positive edge of the clock. This is true actually. This is true. Why? Because see here you can see there is a RST signal at this point. But since this RST has a, it must be synchronization with the clock positive edge. Okay, that means at this point of time, you don't see any kind of positive edge of the clock. That means whenever RST is there, RST has come, at that time only the clock has to be there. If the clock is not there, then RST does not have any impact. That is what synchronization. The RST is not synchronization with the clock signal. The RST is not synchronization with the clock signal. That's the reason why it is not following the RST. It is simply follows as it is in this way. That means, as you can understand that when now RST should be there at what? The clock signal, clock positive edge. That means RST has only impact whenever the RST should be at the positive edge of the clock. Okay, that means whenever there is a positive edge of the clock, at that time the reset signal must be high. Then only it can make the output is equal to 0. In the previous case, it's not like that. Irrespective of the clock signal, wherever you see the RST, the output is 0. But here, RST does not have any impact. It's completely depending upon the clock signal. Okay, that's the reason. Okay, now look at this one. Now, what about the next one? There is a positive edge, there is a 0 is there. Okay, let's go to the 0 here. Okay, this will go 0 here. Okay, now this is available to the next positive edge of the clock. Okay, here also the RST does not have any impact. You look at this one, RST does not have any impact. Okay, RST does not have any impact. Okay, now look at this. Now here we can see there is a positive edge of the clock. According to the positive edge of the clock, it must be go high. Okay, so look at this one. You see the positive edge of the clock, but you see what is happening here. RST is available at what? Exactly at the positive edge of the clock. That means now it has an impact of making 0. Not necessary that the edge is available. Not necessary that edge of the RST is available at the edge of the clock. Not necessary. Okay, but what it is required at the positive edge of the clock, if the RST is available, then it is impact. Okay, so this is a positive edge. You see the RST, instead it is going high, it will remains 0. It remains 0 as long as the RST is high. Okay, only this duration only. Please observe this. Only this duration only. This will be 0. Now at this point of time, RST is 0. Therefore, is there any clock edges here? No. Therefore, this will be continuous to the next positive edge of the clock. Then again, because RST is not there, clock is available. Therefore, definitely it will go in. Are you getting the point? So what is the conclusion here? First, you have to give the priority to the clock. and then give to the priority to the RST. Then, of course, based on the DN, we have to find the DN. Okay, if the reset is not there, sorry, if the clock is not there, irrespective of the reset signal, irrespective of the DN signal, the value of this one is D out, previous value. If the positive edge of the clock is there, okay, if this is logic 1, whatever may be the DN it is, the output is 0. Did you guys this point? The positive edge is there, and that too, high level is there. Now, what about here? For all other cases, irrespective of this one, the value of this one is, I'm so sorry. What is this one positive edge? Okay, let me. What is we can write it here to make this DN positive edge, very good, positive edge, and 0, very good. Now, whatever the DN you give here, the DN will be transparent. Very good. Next, what is the last case? For any other cases, irrespective of this one, it's a D out. Okay, so the intentionally I'm writing the clock signal is the first, then I'm writing the RST. But here, what I have written first, RST. I hope clearly understood the synchronous and synchronous reset, right? This is called asynchronous. Sorry, it is a synchronous, right? This is a asynchronous reset. Is the point is clear to everyone? Okay, so quickly let us modify this program and we can leave. What we can do? What modification that let me give? The topest priority will give it to clock signal. We don't worried about reset signal. Okay, just I want to remove this one, right? As simple as that. I don't want to see any changes of this one, it will go. Okay, whenever see a positive edge, then enter into the block. In that the positive edge of the clock, you see the reset, then output is 0. If you don't see any RST, then DN is equal to D out. Just remove that positive edge of the reset, that is enough. Am I right or not? Okay, yes, therefore this is what we can see. Whenever you see a positive edge, you enter into this one, and in that positive edge, you see any kind of RST is high, then make it 0, or otherwise make it otherwise, depending on, since it is a positive edge, the transparency is occurred. If it is not following any kind of this case, the previous value will be whole square. Right? As simple as that. Okay. So with this, we stop this the theory part of this one. We will do the practical part in the next class.